diode, right? You should communicate. Okay.
Yes, ma'am.
We have discussed about the Jenner diode, right? Jenner diode is voltage regulator. How it will behave, we have already discussed about that one. Yes or no?
Yes, ma'am.
So, what was the last portion? If you remember, depending upon the input voltage and your load resistance, four cases were possible. I have told you that part. Yes or no?
Yes, ma'am.
What are the cases? What are the cases?
VI, fixed VI and fixed RL, fixed VI and variable RL, variable VI and fixed RL, and variable VI and variable RL.
Right. So we will discuss about those cases. Okay. Today we will discuss about those four cases. So we have discussed about Jenner diode is voltage regulator. Right. So now we will start with these cases. Okay. Fixed VI, fixed load resistance, fixed VI variable load resistance, variable VI fixed load resistance, and both variable. Okay, so coming to the first one, that one is fixed VI and fixed load resistance. Okay, so here it is fixed VI and RL means RL is also fixed, VI is also fixed, both are fixed. Okay, we will start with this one. Okay. So first of all, as we have already discussed in the previous class, you can go through the previous class. Jenner diode is voltage regulator circuit. This, we have already discussed how this circuit looks like, right? Here I have already told you this R is this R is what? This resistance R is called as
Current
Current
limiting
limiting
resistance.
resistance.
right. Here this is the place for your Jenner diode VZ, right? And this is load resistance RL. Same thing we will depict here. Okay, now according to this input voltage source and your load resistance, we will discuss the four different type of cases. So first case is both are fixed, means this will have some fixed value and this RL will also have some fixed value, right? So we will discuss about this one. Now this is the same circuit we have designed. Here the Jenner diode will be placed. So how it will placed, if you remember, what Jenner diode should always be connected in which manner? Jenner
Reverse.
diode should in reverse biasing mode, right? So like this, it should be connected, right? This is the symbol for Jenner diode, right? So first, this will be the circuit, but first, how will you analyze this circuit? First step is to determine the state of the Jenner diode by removing it from the network and calculating the voltage across the resulting open circuit. So our first step is to remove this Jenner diode from here, right? Now we will make this as open circuit. Okay, now we will proceed with the circuit analysis. So we will by using this circuit analysis we will find out the state of the Jenner diode, means the condition for on and off. Okay, so now how will you find out? First we will apply KVL. Okay, first we will apply KVL in this loop. As this is open circuit, no current will flow. Yes or no?
Yes, ma'am.
Open circuit means current flow is not there, right? So now the current will move in this manner. Yes or no?
Yes,
Current will
ma'am.
move in this manner, right? So now we will apply KVL throughout the circuit. Now if I apply KVL, this will be negative to positive VI minus I into R minus I into RL, because this is the only current flowing through the circuit. Yes or no?
Yes, ma'am.
So I'm applying KVL in this manner. So it will be VI minus IR minus I into RL equals to 0. Yes or no?
Yes, ma'am.
Yes, ma'am.
Now from this equation I can find out the value of I, current across this circuit, that will be VI divided by, I am taking common I from IR minus IRL, so VI divided by R plus RL. Clear?
Yes.
Yes.
This much clear? Now I'm just analyzing the voltage. I can say, suppose the voltage across this Zener diode I am denoting as V, only V. Okay, this open circuit here. This voltage drop across this point is, this two terminal is V. Okay, now whatever voltage drop occur here, that will be same as VL or voltage drop across RL. Yes or no? Because
Yes, ma'am. Parallel
in
connected.
right, because in two parallel path the voltage drop will be same, right? Whatever V1, that will be V2, right? So V1 equals to V2, the two parallel path voltage drop will be same. So now if I say this is V equals to VL, right? So now that will be, suppose the current is flowing right now, the current I is flowing through this RL, so it will be I into RL. Yes or no? This I is flowing through this path. Yes or no? So I can say VL equals to I into RL. Yes or no?
Yes, ma'am.
Now
Yes.
I, in the place of I can put this value VI divided by R plus RL.
Yes, ma'am.
VI divided by R plus RL whole into, there is RL. RL. Are you getting my point? So this is nothing but the voltage drop across this diode position, Zener diode position, or across this Zener diode. Yes or no? And that is
Yes,
the
ma'am.
voltage drop across this load resistance drop. Now, how will you find out the state of the Zener diode? If you remember, if voltage is less than Vz, then diode is off. We have already discussed that part in the previous class, right? From the characteristics itself, we have already discussed that one. Yes or no? Because Zener, Vz is the nothing but the breakdown part, right? So it looks like the reverse biasing characteristics look like this. So this is Vz. Before Vz we are saying that Zener diode is off. Now after Vz diode is on. Yes or no?
Yes, ma'am.
Current is flowing through the diode, right? So that will be Vz, but before Vz or less than, this is V less than Vz. V is less than Vz, diode is off, correct? Correct or not?
Yes, ma'am.
Yes, ma'am.
Yes,
So
ma'am.
same thing will apply here. Okay, and this is the V, right? So if this V value is less than Vz, then the Zener diode will be off, and if V is greater than or equals to Vz, then diode will be on, right? Same we will depict here. Now we will find the second step. The second step is to substitute the approximate equivalent circuit and solve for desired unknowns. Okay. Now we will substitute the approximate equivalent circuit and solve the desired unknowns. If you remember, what is our approximate model? I have already discussed in the same circuit. If you remember, first of all, whenever the diode is off, we are just convicting it with one off state on state. মনে হচ্ছে না নাই? Off state on state মনে হচ্ছে না নাই? This one, right? Whenever Zener diode is in on state, we are, the equivalent circuit is this. This one is the equivalent circuit. When diode is in on state, we are representing it with one what? With one what? This one is what? Huh?
PN junction normal diode.
PN junction normal diode.
Ma'am, it behaves as a battery.
Right, it behaves as a voltage source or battery. When it is in off state, we are this equivalent circuit. In this equivalent circuit, we are taking this as a simple open circuit, IZ equals to 0. ଆରେ ତମାନେ ଯେତିକି ଆଗକୁ ଯାଉଛ ସେତିକି ପଛ ଗୁଡାକ ଭୁଲି ଯାଉଛ ନା କଣ? Yes or no? This one is from the previous class itself. Turn your page and see. Remember or not?
Yes, ma'am.
Right.
Yes, ma'am.
So same thing we will apply here. Okay. Now when V is less than Bz, it means what? When V is less than Bz means diode is
Off state.
Off.
so this is off state. So in the off state, as the equivalent circuit we have already discussed, this will behave as one open circuit, right? We will represent this as open circuit only. So now we have represented as open circuit. Now for this circuit analysis, you can say IZ equals to 0. Yes or no?
Yes,
Because
ma'am.
diode is in off state. Now if you go for the KCL, if you go for KCL current analysis, so current entering, the sum of the entering current equals to sum of the leaving current from the node. Yes or no?
Yes, ma'am.
So suppose this one is the node A. Okay. Now at this node, IR is entering, IZ and IRL are leaving current, or simply I can denote this suppose as IL. I'm denoting it as IL. Okay. IR is entering, IZ and IL are leaving. Yes or no?
Yes, ma'am.
So IR equals to IZ plus IL. This statement is correct.
Yes, ma'am.
Now
Then
as
IZ
IZ equals to 0, so IR equals to IL.
Yes,
Yes,
ma'am.
ma'am.
Now IR equals to IL, already we have derived it as VI divided by R plus RL. Yes or no? VI divided by R plus RL. IR,
Again.
because that is the only current flowing through the circuit. That will be same. IR equals to IL equals to VI divided by R plus RL. Same condition as we have already derived in the first case. This is the same as the first case. First step. Yes or no? This statement, this step is same as this first step, right?
Yes, ma'am.
Now coming to the next one. V is greater than equals to Vz. It means V is greater than equals to Vz means diode is
On.
on. Now we are going to the on state. So as we have already derived in this equivalent circuit, on state means V is greater than Vz. On state रे कौन होतला? The equivalent circuit, here it is the battery. It will be denoted as battery. So same, we will represent this with one DC source. Yes or no? ठीक अछि?
Yes, ma'am.
Yes.
Now in this circuit apply KVL. Here you can apply KVL in loop number 1. You can apply KVL. So this will be VI minus I into R. Suppose this current through this I resistance equals to I subscript R. Okay. Current through this resistance is I subscript R. Right. So I can write VI minus IR into R minus VZ equals to 0, because this is the positive terminal, this is the negative terminal. I have denoted as minus VZ equals to 0. ठीक अछि?
Yes, ma'am.
So now I can say IR equals to VI minus VZ divided by R. From this equation I am just deriving IR value. ठीक अछि?
Yes, ma'am.
Now from here, from this output angle, you can see this from this node IZ, and here it is IL, right? So IL into RL will be VL, correct? IL into RL will be VL, voltage drop across this load. Yes or no? Voltage drop across this load resistance VL will be IL into RL.
Yes, ma'am.
So now from here I can derive IL equals to VL divided by RL.
Yes, ma'am.
Yes, ma'am.
Now VL can be represented with VZ because the voltage drop across this load, VL will be same as VZ. Yes or because parallel
Yes,
path
ma'am.
already we have discussed VL equals to VZ. So I can represent this VL as VZ divided by RL. Correct? Correct or
Yes,
not?
ma'am. Yes, ma'am.
Okay, now
Okay.
going. Hela samastha na kar doubt ochchedi pacharo. Are you having any doubt? Are you having any doubt?
No, ma'am.
Okay, so we have already derived our current across the resistance, current limiting resistance IR, and we have already derived current across the load, that is IL, right? Now by applying KCL, the remaining is IZ only. We are having three currents. One is IR, one is IZ, and one is IL. So we have already derived this IR and we have already derived this IL, right? So remaining is IZ. By using KCL, we can find out IZ.
Yes, ma'am.
IZ
Yes,
I,
ma'am.
equals to IR minus
I,
IL
yes,
because
ma'am.
IR is the entering current at this node. IZ and IL are leaving. IR is entering, right? And IZ is leaving as well as IL is leaving. Yes or no?
Yes.
So same thing from here, this equation I am deriving IZ equals to IR minus IL. Now IR we are having VI minus VZ divided by R. Similarly IL equals to VZ divided by RL. By applying these two you can find out the IZ value. Correct? Clear or not?
Yes, ma'am. Yes, ma'am.
Yes.
So we have already derived the desired unknowns. Okay. Cover. Now the power dissipated by this Jenner diode is determined by PZ. Okay. PZ, power dissipated by the Jenner diode equals to VZ whole into IZ. VZ you can be known, then you can find out IZ, VZ into IZ. Right, and PZ must be less than PZM. Always remember this term PZM. That will be one specified value. Okay, that is the maximum. You can write down maximum power dissipated by the Jenner diode. Maximum power dissipated by the Jenner diode. Okay, always remember this PZ should be less than PZM. Okay, because this is the maximum power rating gote thibo tatu obviously come power dissipate hoibo. Yes or no?
Yes, ma'am.
Clear?
ଏଠି ପିଟା ଯୋଉ ଦେଲେ ଏଟା କାହାର ପିଟା ମାନେ
Power dissipated by this Jenner diode. Power dissipated by Jenner diode.
okay, ma'am.
Now coming to the next one. First case solved. Next one is fixed VI variable RL. Fixed VI variable RL. Okay. Now for fixed VI variable RL, variable RL means obviously you know this term whenever you are using variable resistance or resistor, always we are using this arrow mark, yes or no?
Yes, ma'am.
This arrow mark denotes that this R is varying and it must have some range, yes or no? Jota bhi tame rheostat use karucho, if you remember in the lab there will be one specification 0 to 15 kilo ohm or 0 to 15 ohm like that, yes or no? Are yes or no? ନା କେବେ
Yes,
ୟୁଜ
ma'am.
କରିନ? ଶୁଣିଛ ନା ଶୁଣିନ?
ମ୍ୟାମ୍ ଇନଷ୍ଟ୍ରୁମେଣ୍ଟ ଗୁଡାକ ଲେଖା ଯାଇଥାଏ
Right.
ତାର
Range, there will be a range. Okay, as this RL is variable here, it will operate in a specified range of register values to ensure the state of the Zener diode is on. Okay, this will control whether your Zener diode is remaining in on state or off state. How according to this condition of Zener diode will vary. We will study about that one, right? Okay, now if RL is too small, okay, now RL must have some range. Okay, if I say RL must have some range, suppose I'm telling you this is varying from 10 kilo ohm to 100 kilo ohm. Okay, suppose I'm telling you this is the value of our RL. Okay, suppose if I'm saying this value is very low, suppose RL, it is operating in some range. If RL is too small, then what will happen? VL will be very small, because VL, I will say VL, voltage drop across this load, will be IL into RL. Yes or no?
yes ma'am.
IL
Yes.
into RL. So if RL is very small, then VL will be very small, directly proportional.
Yes ma'am.
Right. So what will happen if VL is very small? VL will be equals to VZ, yes or no? VL will equals to V or VZ. If I denote it as VZ, same potential achi, parallel path re same voltage drop rahibo, right?
Yes ma'am.
So this will, I can say this is equals to VZ. If VL is very small, it means VZ is also very small. VZ, or I will say this we have already denoted as V only, right? We have already denoted it as V. Okay, we are comparing with drop across this Zener diode will be very small. Yes or no? If that is very less than your breakdown, if this V is very less than our VZ, we are comparing V with VZ, right? Then the Zener diode will be off.
Yes ma'am.
So this will cause this Zener diode to go off. Now to keep this Zener diode in on position, what we will do, we will see. Okay. It have off ହେଇଯିବ ଯଦି ୟାର value କମ ହବ. If RL is having very small value, then voltage drop this across this RL will be very small. The voltage drop across this RL will be equals to voltage drop across this Zener diode. That will be very small. If that is very small, means less than the breakdown one, then Zener diode is in off condition. Now what I will tell you is to determine the minimum value of RL for which we will make this Zener diode on, for which this Zener diode will remain in on state. Okay, we will find out the minimum value of RL for which this Zener diode will remain in on state. Are you getting my point? Yes or no?
Yes ma'am.
So how will I find out? We will first consider ଆମେ उल्टा पटे ଯିବା, reverse direction रे ଯିବା. Okay, our conclusion कोण? We have to find out this RL or the minimum value of RL for which the Zener diode is in on state. Okay, now we will consider this Zener diode in on state. Okay, first let's take Zener diode is in on state, means the voltage drop across this Zener diode, I am taking it as VZ, that is equals to VL, that will be I into RL, we have already decided, and IL we have I we have already derived, that will be VI into RL divided by R plus RL. Yes or no? When it is in when we are considering this open, we have already derived this I value, I into RL. Yes or no?
Yes ma'am.
Correct?
Yes.
Right. So we will find the minimum range of RL. From this we can derive VZ equals to VI divided by R plus RL minimum into RL minimum. I'm just putting the minimum range. If I will take RL, the minimum value, then this will be VZ. Yes or no? Yes or no? We have to derive.
ଆଉ ଥରେ ଟିକେ କରିବ
Yes, ma'am.
back
Now for RL minimum, we are deriving VZ equals to, we have already derived this one. In the previous state already we have derived in the from the first one, V equals to VL equals to VI into VI divided by R plus RL into RL. Okay, same thing. This same thing. This is the I value. I value VI divided by R plus RL. Right. It's the same thing. टा मैं यूज करची VI divided by R plus RL into RL. Same देखो. Same जिनसा टा मैं already आउथरे लिखी ची. Are you getting my point?
Yes, ma'am.
এটা বুঝি পারলো তো সেইটি that is your VL value that is equals to VZ. Yes or no? For this circuit, whatever it is VL, same parallel path रे that will be equals to VZ. Yes or no?
Yes, ma'am.
So same thing I have written VZ equals to this much. Yes or no? Now I'm just putting RL equals to RL minimum. I'm just taking the minimum value of this RL. This will operate within some range. This is the minimum range. This is the maximum range. Right? Suppose I'm taking RL equals to minimum. RL minimum, I'm taking VZ equals to VI divided by R plus RL minimum whole into RL minimum, because we have to find out the RL minimum value for which the Jenner diode is in on, which will make the Jenner diode on. Yes or no?
Yes, ma'am.
We are determining the minimum value of RL which will make the Jenner diode on. Right? For that we have to consider RL minimum here. Yes or no?
Yes, ma'am.
जरा डाउट थिला बुझी पारलो ना प्रॉब्लम किछ हैला
नहीं मैम बुझेला.
बुझेला तो नाउ I will find this RL minimum. From this equation you will find RL minimum. What I am doing here is I am just multiplying this R plus RL minimum in this side. Okay, VZ into R plus RL minimum equals to VI RL minimum. Yes or no? I am just multiplying both the sides with R plus RL minimum. Multiplying both sides by R plus RL minimum. Am I clear?
Yes, ma'am.
Now just open this bracket. This will be VZ into R plus VZ into RL minimum equals to VI into RL minimum. Just open this bracket. Open karo bracket. What will you get? VZ into R plus VZ into RL. नीचे नीचे करो जल्दी quickly. RL minimum equals to VI whole into RL minimum. Yes or no?
Yes, ma'am.
Yes.
Now from here I am just taking this RL minimum to one side. Okay, just bring this RL minimum to one single side. This will be VI RL minimum minus VZ RL minimum equals to VZ into R. Are you getting my?
Yes, ma'am.
So from this I can take RL minimum common. The remaining will be VI minus VZ. So RL minimum whole into VI minus VZ is equals to VZR. From this you can divide RL minimum equals to VZR divided by VI into VZ. Clear or not? Clear or having any doubt? If you are having any doubt, then quickly ask. Solve करो जदि ना करी पारुचो पचारो. I'm just
मैम ये जो VZ का जरा ब्रेकडाउन वोल्टेज नहीं.
हाँ. VZ into R. Here I am taking this is the voltage across the Zener diode. Okay, because that is breakdown टा ही तमरो सेटा गोटे particular point ताठ हो अधिको किछि voltage नाही. VZ is the only voltage you will find across this Zener diode, isn't it?
Yes, ma'am.
After that only current will increase.
Voltage remain constant after
Not
this.
increase.
And
Well, this
current
is the constant voltage. Current
current
अरे तमरो कौन हो?
voltage remain constant.
हाँ, obviously reverse bias characteristics केमती थिला एमती ही थिला तो हाँ ना नहीं.
Yes, ma'am.
This is
Yes,
VZ because this is the only voltage. Okay, after this only this is you will find the sharp one here. In case of Jenner diode, you will find the sharp one, right? So this is the only voltage you will find. After that, the current will only increase. VZ will remain constant. I'm already first class discussion करचे.
Yes,
Before
ma'am.
that,
हाँ.
the Jenner diode is off. So this is the only voltage you will find across this Jenner diode, right? Because at this VZ, the diode is turning on. Before that, the diode is off. Yes or no? This is the voltage axis. Before this VZ, जहाँ भी एटी voltage value -3, the diode is off, right? Only at Vz the diode is turning on. Yes or no?
Yes, ma'am.
So you will find out RL minimum equals to Vz into R divided by Vi minus Vz. Am I clear? Clear or not?
Yes, ma'am.
Now you can go for the current value. Whenever, as I have already discussed here, VL equals to IL into RL, right? So I am putting RL equals to minimum. Okay, then IL will be maximum. Yes or no? If the resistance value comes, current across this resistance path will increase because
Yes, ma'am.
resistance will is decreasing. Yes or no?
Yes.
So IL will be maximum. When RL is minimum, I can say IL will be maximum. Am I correct or not?
Yes, ma'am.
So IL maximum will be VL divided by, I would say, RL minimum. Correct or not?
Yes, ma'am.
Now, in case of VL, I can write VZ. In case of in the place of VL, I can write VZ because VL equals to VZ. VZ divided by RL minimum. बुझिगला बुझिगला ना नहीं? Now coming to the
Yes,
current
ma'am.
analysis. Come to the current analysis. This is the node A. Okay. This is IR and this is IL. Right. This is node A. Current analysis will be IR equals to IZ plus IL. Yes or no?
Yes, ma'am.
Yes, ma'am.
IR equals to
Yes.
IL plus IZ. Right. So you can say IR equals to IZ minimum plus IL maximum. If I say this is our IL, we have derived IL as RL minimum, IL will be maximum. Yes or no? RL minimum, that's why IL will be maximum. Right. If we are taking IL as maximum, then IZ should be minimum because we have to keep this IR constant because IR will be a constant value. Yes or no?
Yes, ma'am.
So if we are taking when IL equals to, you can say IR equals to IL plus IZ, and in this equation, if IL equals to maximum or when IL equals to maximum, then we can say IZ is minimum. Right? By using this equation, you can find out your IZ minimum.
Yes, ma'am.
Right. So now you can, because you know this IR value, IR equals to VI minus VZ divided by R. Vi minus Bz divided by R. In this, by using this KVL in this equation, you can find out this IR value, right? And IL maximum we have already got, right? So both are known to you. From this equation, this unknown value, that is IZ minimum, you can find out. Yes or no?
Yes.
Yes, ma'am.
Okay, so IR hegala, IL hegala, and IZ minimum bhi hegala. Now take the condition for RL maximum. We have completed for minimum. Now take the condition for RL maximum. RL maximum. What will happen when RL is maximum? IL will be
Minimum.
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 So what will be this equation? IR equals to IL minimum plus IZ maximum. Correct?
Yes, ma'am.
If IL is, I'm just changing. If IL is minimum, then IZ will be
Maximum.
maximum. Very good. Right. So you can find out IZ maximum by using this equation. Now, if we are saying RL maximum, how will you find out RL maximum? How will you find out RL maximum? That will be VZ divided by IL minimum. Yes or no? VZ divided by IL minimum, you can find out RL maximum. Yes or no? I'm just keeping
Yes.
here it will be BL,
Yes,
but in
ma'am.
case of BL, I can write down VZ, right? VZ divided by IL minimum. Correct or not?
Yes, ma'am.
Yes, ma'am.
Right.
Yes, ma'am.
So for the power, PZ maximum will be what? IZ into VZ. So VZ is fixed, so this will be maximum. IZ will be maximum. This one. Yes or no?
Yes, ma'am.
So you
Yes,
can
ma'am.
find out your PZ maximum by using IZ max into VZ. Am I correct?
Yes, ma'am.
Okay.
Yes, ma'am.
So by using these formulas, you can derive your variables or whichever value is unknown to you. You can derive those values, right?
Yes, ma'am.
Coming to the
Ma'am,
next case,
ma'am, how to find IL minimum?
IL minimum.
Yes, ma'am.
See, we have already discussed that one. I'm just repeating. As RL minimum is there, whenever you are using VL equals to IL RL. So IL minimum बचला ना IL maximum बचला मतलब
IL minimum. Ma'am, RL maximum is equal to VZ by IL minimum.
हाँ एक लिखा है जी.
Yes, ma'am. Yes, ma'am.
Right, by using, if your RL maximum is given, you can find out IL minimum. Or by using this
Yes, ma'am.
equation also you can find out IL minimum. And for IL maximum you can use RL minimum. If you are using RL minimum here, you will find IL maximum. Right? If you use IL maximum, RL maximum here, you will find IL minimum. Clear?
Yes, ma'am.
So now coming to the next one, that is variable VI into fixed with fixed RL. Okay, variable VI with fixed RL. Here RL is fixed. Now you can say VI is variable. That's why you given one arrow mark. Now VI is variable means it will have VI is variable means it
Variable
will
voltage.
have some range.
Variable voltage.
Sorry,
Variable voltage.
variable voltage. So now it will have some range. Range I can denote is as VI minimum to VI maximum. ସେଠି ଯେମିତି କରୁଥିଲେ RL minimum to RL maximum. ଏଠି ସେମିତି VI minimum to VI maximum. Yes or no?
Yes, ma'am.
This
Yes,
will be
ma'am.
the range. So here VI is variable which will have some range, right? So now by according to this range we will find out for the case which will keep this Zener diode at on state, right? So what is the condition for Zener diode to be on? V should be greater than equals to VZ. This is the condition to keep the Zener diode at on state. Yes or no?
Yes, ma'am.
Yes, ma'am.
Right. So the minimum voltage required to make this Zener diode on. What will be the minimum voltage required to make this Zener diode on? What is the minimum voltage required to make this
E
Zener
equal to
diode on?
VZ.
V equals to Vz. That will be, you can find out Vz. Apply KVL in this equation. You will find out Vz equals to KVL use करो Vi minus IR minus Vz equals to 0. Right? From using this, by using this equation, you can find out Vz equals to what?
VI minus
Vi
VI
minus
minus
I.
IL.
Vi minus I into R. Vi
Yes, ma'am.
minus I into R. Now, what is the R value? Sorry, what is the I value here? I can say Vi into, I can directly write Vi into RL divided by R plus RL. Is it correct or not? Vi into RL divided by R plus RL. ठीक अच्छी ना नहीं?
Yes, ma'am.
ठीक अच्छी तो? Already हमें derive करी चेटा first case रे.
Yes, ma'am. Yes, ma'am.
Right? So now, minimum value find out karo. What will be the minimum value? How will you find out Vi minimum? Vi minimum. Vi minimum. Here it is Vi. Find out Vi minimum. See, from this, I have written Vz equals to Vi RL divided by R plus RL. तो ମୁଁ एवटू खाली Vi find out करी परिबी. ए equation रो by using this equation I can find out Vi equals to Vz whole into R plus RL divided by RL. ठीक अच्छे ना नहीं? ये टर्म टा एपटे नहीं कि multiply कर देली उल्टे की.
Yes,
ठीक
ma'am.
अच्छे ना?
Yes, ma'am.
So now from this you can find out
Yes, ma'am.
Vi minimum. This is your Vi minimum. Vz into R plus RL divided by RL. Why this is minimum condition? Because here you are using Vz, right? Any value less than Vz, your general diode will be off. Any value greater than Vz, it will only keep in Vz.
Yes,
This is the
ma'am.
minimum value. V should be greater than equals to Vz. V equals to Vz is the minimum value. Yes or no? So we are taking here Vz, right? अरे बुझी पाला ना बुझी पाला नहीं बुझी पाला तो कौन पाएगा
Yes,
minimum
ma'am.
condition,
Yes, ma'am.
right? So for maximum, Vi maximum, how will you find out Vi maximum?
मैम मैम जो VI मिनिमम रे जो डिनोमिनेटर जो RL ରହିଲା ମାନେ ସେଟା RL maximum ହବ କି?
नहीं ऑलरेडी सेटा ही को तो बुझेली तुमको
मैम,
एटी
R
आर
टा बोधे change
कांस्टेंट
हबो।
नहीं आर टा एटी रेंज ही नहीं एटी फिक्स्ड आरएल आरएल इज
मैम
वन
yes ma'am,
फिक्स्ड
मैम एपटे जो R टा जे सेटा मैक्सिमम हबो कि एटा जो
कोठी पे एटी आर एल और आर दीटा जाको फिक्स्ड आरएल इज आल्सो फिक्स्ड आर इज ऑलवेज फिक्स्ड R is always the fixed value, current limiting resistance.
okay.
Only we are according to VI and RL, we are studying the cases. RL can be one variable value and that can vary within a range. But for this case, we are taking fixed RL. We are taking fixed RL. Why I am telling you this VI equals to VI minimum? Why? What is the reason I am telling VI equals to VI minimum? Because we are using VZ here. Right, V equals to Vz is the minimum value to make this general diode on. If I am taking Vz minus 1 or Vz minus 2, it means general diode is in off condition. Yes or no? If Vz value कम है, then it will be off condition. We are here using the Vz value. That's why I am taking this is the minimum value to make this general diode. Here it is the general diode is in on condition. Right? If you are using VZ here, it means whatever the value you are finding, it is the minimum value. Anything greater than this, VI will be increased. Yes or no? So what
Yes,
will
ma'am.
be the range for maximum? How will you find out?
Vi minus Vi minimum.
How will you find out the maximum one? VI maximum. Remember this IZ max value? IZ max. You can say IZ max equals to IR minus IL. Right?
Yes, ma'am.
So this VI maximum is limited by maximum Jenner current, that is your IZ max. Right? So IL is fixed here. IL is fixed here, yes or no?
Yes, ma'am. Fixed.
Now you can control this resistance current to make this as maximum. Yes or no? If you want IZ equals to maximum and this is fixed, then you have to vary this current across this resistance. Yes or no? So you can take this at its maximum limit, IR max. Right? By using this, you can find out VI max equals to, or I can say by applying KVL in the same loop. In the same loop, if I apply KVL, okay, in the same loop, okay, if I apply KVL, that I am taking it as VI max minus VR max minus Vz equals to 0. Now, if suppose I am taking Vi max equals to IR max whole into R, current limiting resistance R, plus Vz, that will be correct, right? Yes or no?
Yes, ma'am.
So this is called as our current limiting resistance. If you remember, I have already told you current limit କରିବା ପାଇଁ se resistance ଟା use होइଛି, that will control the current, right? So that's why I am taking it here. It is IR max into R plus Vz. So this will be your VI max, VI mean and VI max. Clear?
Yes, ma'am.
Got it or not?
Yes, ma'am.
So should I go for the next one?
Yes, ma'am.
Should I go for the next one or not?
Yes, ma'am.
Yes,
Okay.
ma'am.
Yes, ma'am.
So next case is which one? What is our next case? What is our next case?
Both Vi and RL are variable.
Both Vi and RL are variable, right? So I'm just taking variable Vi and variable RL. So again, this will be variable, right? So for this, both are having some range. Vi is also having some range, RL is also having some range. So you can take R minimum equals to Vi max minus Vz divided by IR max, again R maximum you can take as Vi minimum minus Vz divided by IR minimum. So to keep Jenner diode on and to maintain constant voltage across the load, the condition for this case is IR should be greater than equals to IZ plus IL. Why? Because here it is IR, if you remember, by using KCL, we have already derived this equation that IR equals to कौन ए नोड रे KCL पके के मैं कौन फाइंड आउट करथिले IR equals to
IZ plus IL.
IZ plus IL, right? So here I am taking greater than equals to. Why greater than equals to symbol is used here? Because if this drops below, means that AR value ta kami jibo, then what will happen? IZ, if you are, this is not greater than equals to IZ plus IL, then what will happen? IZ jodi drop bhi karibo, then IL vary karibo. Jodi IL is minimum, then again you will find this open circuit. So the IL maximum hela, then also it will cause some problem. That's why we have to take IR is greater than equals to IZ plus IL, so that this Jenner diode will remain in on state. Are you getting my point? Yes or no?
Ma'am,
Yes,
out
sir.
जदि IL टा तमरो मिनिमम हे जाउची वैल्यू कोन हबो IZ टा मैक्सिमम हबो कि नै जदि IL टा
Yes, ma'am.
मिनिमम हे जाउची देन कोन हबो IZ मैक्सिमम हबो तो मैक्सिमम करंट फ्लो across this resistance karibo, so again it will hamper this circuit, right? So even if IZ if you are taking IL as maximum, then what will happen? जदि एटा मैक्सिमम नबा IZ minimum हे जिवो, minimum
Minimum.
current जदि nearly equals to 0 हे गला current flow ताले एटा open circuit हे जिवो,
yes ma'am.
Yes, ma'am.
right? So both cases रे voltage regulator failure होबो है ना नहीं?
Yes ma'am.
So that's why we have to make sure that IR should be greater than equals to IZ plus IL. It can be equal or it can be greater than equal. Okay, because we have to keep this voltage is greater than equals to VZ, right? जदि IZ minimum हे गला भी VZ minimum हे जिवो, जदि IZ minimum हैला ताले VZ minimum हबो कि नहीं? VZ equal, अरे VZ टा minimum हबो कि नहीं? V equals to IR, right?
Yes
जदि
ma'am.
I टा minimum हो जे V टा भी minimum हबो ना?
Yes, ma'am. Yes, ma'am.
तो जदि ताठू कम हे गला VZ रु कम हे गला then कोन हबो? If it is less than VZ, then what will happen?
Offset.
Off
Ma'am,
state को पड़ेबो,
offset.
ऑफ स्टेट को पड़ेबो, तो तुमको कौन करियर अछि? जनरल डायोड को ऑन कंडीशन रे रखिबार अछि, so that the voltage will be regulated. Yes or no?
Yes ma'am.
Yes, ma'am.
So coming to the example, okay, suppose in this circuit, this is the example you can write down in another segment. तमे निजे आउथरे draw करो. Okay, here the value is 1 kilo ohm, R equals to 1 kilo ohm, RL equals to 1.2 kilo ohm, RL equals to 1.2 kilo ohm. Okay, now write VZ equals to 10 volt, VZ equals to 10 volt,
Ma'am, RL केते कहले?
it लिखा है जबरा 1.2 kilo ohm. My screen is not visible to you.
Ma'am, one टा ma'am ठीक से देखते हैं.
1.2 kilo ohm. PZM equals to 30 PZM equals to 30 milliwatt, 30 milliwatt. PZM equals to 30 milliwatt. Okay. This much is given. Here the Jenner diode is given already. Okay. This is the Jenner diode. General diode is given, okay, like this. Okay, now the VI supply is given as 16 volt. Supply is given as 16 volt. Okay, I am repeating. VI equals to 16 volt, R equals to current limiting resistance, R equals to 1 kilo ohm. For Zener diode, VZ equals to 10 volt. PZM, maximum power dissipation, is given as 30 milliwatt and RL equals to 1.2 kilo ohm. You have to find out, write down the question. Write down the question. You have to find out VL, VR, current across the Zener diode IZ, and PZ. PZ. Are you getting my point? Are you getting
Yes,
my
ma'am.
point or not? Now,
Yes, ma'am.
second bit is you have to repeat part A. Repeat A with RL equals to 3 kilo ohm. With RL equals to 3 kilo ohm. With RL equals to 3 kilo ohm. Am I clear?
Yes, ma'am.
So
Ma'am,
you have to do this. Screenshot नहीं जाओ, এটা तुमको करके आने रोज.
Ma'am, PZM car or power?
Zener diode ro, Z अच्छी means Zener diode ro.
Maximum power.
Power dissipated
Ma'am.
across this Zener diode, that is PZ. PZM is the maximum power dissipated by the Zener diode. Maximum power dissipated by the Zener diode. We have already derived here. See, I have already written. PZ. This PZ I am writing again. PZ is, you can write down, power dissipated by Zener diode. Okay, PZM is the maximum. PZM is the maximum power. Maximum power dissipated by Zener diode. Dissipated by the Zener diode. Clear?
Yes, ma'am.
That is the maximum value, power value of the Zener diode. ताठू अधिका जाई परिबनी. ठीक अछि, एटा सब बेले सीट रे मेंशन थाए. जेमती गोटे तुम जो कहूँ गोटे बीजेटी लैब रे जब यूज करिथिबो ताले बीजेटी रे कोन गोटे बीटा वैल्यू गिवन थाए माने तार किछ गोटे पैरामीटर गिवन थिबो दैट इज द मैक्सिमम लिमिट गिवन गोटे स्पेसिफिक सीट थाए सब डिवाइस रो गोटे सीट थाए एतिक रेंज भीतर ही ऑपरेट करि परिबो ताठू अधिका जाई परिबोनी राइट दैट इज द मैक्सिमम पावर डिसिपेटेड बाय द जनरेटर एटा सब बेले स्पेसिफिकेशन सेट रे गिवन थिबो क्लियर
Yes, ma'am.
ଆଉ ଡାଉଟ୍ ନାହିଁ ଅଛି ଯଦି ପଚାର
ମ୍ୟାମ୍ ସେ only P ଟା କଣ?
only P, there is no only P, that is PZ, okay. PZ should be less than equals to PZM, always less than equals to PZM. आठू अधिका जाई परिबनी. PZM रो अधिका जाई परिबनी. PZ should be always less than equals to PZM. Clear?
Yes, ma'am.
सोनल
Ma'am.
सतपथी हाँ
ma'am,
Question
आज
ର
slide
screenshot
में
नहीं. क्वेश्चन ର स्क्रीनशॉट नहीं जाओ हाँ को
तो मैम no मैम बाकी स्लाइड का टिके आज रो खाली साइन कर
हाँ तुमको मो नोट्स हैंड रिटन नोट्स गुड़ा पठे देबे एथरे तो तुम इरेज भी बार बार करूछ ना तो मु तुमको हैंड रिटन नोट्स टा पठे देबे ठीक अछि
यस मैम
सोनल सतपथी ओम प्रकाश
Yes, ma'am.
सच्चिदानंद राउत
Present, ma'am.
सुब्रत भूया एब्सेंट निकिता
Yes, ma'am.
तापस
Yes, ma'am.
प्रीति परमिता
Yes, ma'am.
हरीश
Present, ma'am.
आयुष
Absent, ma'am.
आयुष स्वाइन
Ma'am, absence.
Sudipta?
Present, ma'am.